Majority vote treats every noisy rule equally. Snorkel LabelModel learns which agreements deserve more trust. You'll fit Snorkel LabelModel to produce probabilistic training labels from rule votes on reviews. I'm Professor Pi, teaching AI foundations with simple Python. A review dataset can be huge, but hand labeling each review as good or bad takes time and money. Teams often start with rules instead. A review containing great may suggest a good label. One containing awful may suggest a bad label. These rules are fast, but they are imperfect. Weak supervision lets us use those imperfect rules to create training labels. Snorkel is a strong fit because it organizes rule votes, handles abstentions, and learns from how rules behave together. Instead of treating every vote as equally reliable, its label model estimates which rules deserve more influence. A review, such as not good, exposes the problem. A positive keyword rule sees good. A negation rule sees not. Simple majority voting can tie or choose poorly. The label model studies many such patterns and produces probabilities rather than pretending every decision is certain. We will build a small review labeling pipeline. The goal is not to replace careful human evaluation. It is to turn useful domain knowledge into probabilistic labels that can train a later classifier. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. We first need a consistent review dataset and label vocabulary for every rule to share. This snippet creates a small review data frame and imports Snorkel's core labeling tools. The short texts deliberately include clear sentiment, negation, exclamation marks, and one uncovered example, so later rules can agree, conflict, or abstain. Abstain, bad, and good establish Snorkel's expected integer label scheme, while pause and neg keep the keyword logic readable. The printed result confirms that DF contains 13 rows ready for weak supervision. This small dataset is useful because you can inspect why each rule voted, rather than treating the process as a black box. The reviews exist, but the model still needs independent sources of weak evidence. This example turns simple text signals into 4 Snorkel labeling functions. A rule should abstain when its evidence is absent, rather than guessing on every row. So each function returns abstain outside its narrow condition. LF positive and LF negative use keywords, while LF exclaim and LF not represent weaker contextual signals that may disagree with them. The labeling function decorator packages each callable for Snorkel, and LFS preserves their column order. The output confirms that 4 independent rule definitions are ready to apply. Narrow rules are often better than broad guesses, because an abstention tells the label model that a rule had no evidence. Rules are only ideas until we apply them across every review and inspect their behavior. This code applies every Snorkel rule and measures where the rule set needs attention. Pandas LFApplier.apply produces L with 1 row per review and 1 column per labeling function. LF analysis, label coverage, checks whether at least 1 rule voted, while label conflict finds rows receiving different non-abstain labels. High coverage alone is not enough, because noisy rules can still collide frequently. These reviews could stand in for support tickets labeled by operational heuristics. The output shows broad coverage alongside meaningful conflict, which motivates a learned combination instead of blind voting. This inspection also helps you spot a weak rule before it quietly affects every generated label. For more practical lessons on Python, data science, and AI foundations, please subscribe. Those conflicts are exactly where equal voting loses useful information, so we can compare it with learned weighting. This snippet compares equal voting with Snorkel's learned label model on a conflicting review. MajorityLabelVoter predict proba gives the positive and negative rules equal influence, producing a tie for row. LabelModel.fit instead estimates rule behavior from recurring agreement and disagreement patterns in L, with seed keeping initialization reproducible. More N epochs gives optimization additional steps, but costs more training time. It cannot automatically eliminate every dependency between strongly correlated rules. The output shows whether learned weighting moves the positive probability away from majority votes 50-50 result. That shift matters because it captures uncertainty while still using the patterns found across the full review set. Now that the model can estimate trust, we need labels in a form a downstream classifier can use. This code converts Snorkel's learned rule combination into a compact training label table. Rows where every rule abstained are removed with covered, preventing unsupported examples from receiving artificial labels. Label model predict proba returns both class probabilities in train prob. pgood exposes the positive probability, while argmax supplies a conventional hard label when a downstream learner requires one. Keeping train probs preserves uncertainty that majority vote would discard, so a classifier can consume soft targets when its training API supports them. The output displays one review with its probabilistic and hard training labels. The hard label is convenient, but the probability tells you how strongly the rule system supports it. When a team has a small set of trusted human labels, use them to evaluate these generated labels and improve the rules. Human labels reveal where keyword rules miss sarcasm, domain language, or phrases that reverse sentiment. The label model combines the signals you provide, so better and more varied labeling functions usually matter more than simply adding many similar rules. This example shows why weak supervision is more than automated keyword matching. Rules create coverage, conflict reveals uncertainty, and label model turns those noisy votes into more useful probabilistic training data. Try changing N epochs and compare whether the learned probability for the conflicting review remains stable. You can also add a carefully chosen phrase rule. Then inspect whether it increases coverage without creating too much conflict. What practical AI labeling topic would you like to explore next? Share it in the comments and subscribe for more clear Python and data science lessons.